Welcome. My name is Stefan Schwede. I'm a professor of mathematics at the University of Bonn. My area of research is algebraic topology, and recently I've been very interested in equivariant stable homotopy theory. I was scheduled to teach an advanced topology class on global homotopy theory in the summer term 2020, but because of the corona pandemic, our university, like many others, is closed down, and we have to find new ways of doing our teaching. Since my class on global homotopy theory is fairly advanced and it's not likely to be taught very often, I decided to get my lectures videotaped and then make them available for public use. My hope is that this way not only the students in Bonn but also other students worldwide that might be interested can take advantage of this. If that actually happens, it would be a small positive side effect of the corona crisis. At the beginning of this first lecture, like in a regular course, we have to get some administrative things out of the way. I have to explain how this is going to work, and I want to comment a little bit on the prerequisites which are necessary to follow the class. This class is scheduled to take place Tuesdays and Thursdays, and I will try to mirror that by uploading one video every Tuesday and every Thursday during term. This first video was uploaded on April 21st, and the plan would be to continue until mid-July. I also maintain a homepage for this class, so please check that regularly, where you can find details on all sorts of things that are relevant. So I anticipate that the post-production of the videos on top of the actual teaching will take a certain amount of time. And in case I actually completely underestimated how much time this takes, I might have to reduce the frequency or the length of the videos. But my plan would be to have two 60-minute videos every week, and cross your fingers that I'm actually able to produce this material. At this point, I would like to give a special thanks to JDLP, who is behind the camera right now, and who has kindly volunteered to do all the post-production of my videos. I'm also planning to host a weekly discussion and question session using the Zoom communication technology. So this also will be open to everyone. If you're interested in joining that, please check the webpage for information how you can sign up. For those students who are enrolled in the master's program in Bonn, we will have some kind of exam for this class at the end. At this point, however, I think nobody can predict when exactly that's going to be and how it's going to be, but we will find a way to get an exam so that you can take credit for the class. Let me now turn to the mathematics. So this class is on global equivariant homotopy theory. So that means these are equivariant phenomena that exist in a uniform and coherent way for all groups at the same time. All groups will in this class typically mean all compact Lie groups, but it can sometimes also refer to a specific subclass, so such as, for example, all finite groups. Some phenomena that are global in the sense that they exist uniformly for all groups are things like equivariant cohomotopy, equivariant K-theory, equivariant Bordism, or equivariant Borel cohomology theories. This class is classified as Advanced Topics in Topology, and it's actually the sixth class in a whole series of lectures that build upon each other. So in particular, I will assume as background all the basic algebraic topology and homotopy theory, starting with things like singular cohomology, homotopy groups, CW complexes, loop spaces, fibrations, fiber bundles, vector bundles, smooth manifolds, Grassmannians, projective spaces, and Stiefel manifolds. 1 year ago, I taught together with Benjamin Böhme a class on algebraic topology 2, and there we gave an introduction to stable homotopy theory in the non-equivariant context. We used orthogonal spectra as our model. We defined stable homotopy groups. We discussed the stable homotopy category, including its triangulated structure, and we covered all sorts of examples, such as suspension spectra, Eilenberg-MacLane spectra, different kinds of Bordism spectra, tome spectra, free orthogonal spectra, and models for connective and periodic topological K-theory. I will revisit some of these topics from an equivariant, and in particular from a global equivariant perspective. Nevertheless, I think it's quite helpful if you have some familiarity with non-equivariant stable homotopy theory, and if you've already seen at least some of these examples in the non-equivariant perspective. Last semester, I taught another advanced topics class on equivariant stable homotopy theory. So in that class, I concentrated on the case of finite groups, and I only talked about phenomena that are specific to one finite group, and then always the subgroups come up as well. Occasionally, I gave some glimpses on how things have to be adapted if you want to cover compact Lie groups. Also there, we worked in the context of orthogonal G spectra, and the topics we covered were equivariant stable homotopy groups, the Tom-Dick splitting, the Adams isomorphism, all in terms of finite groups. And my personal highlight was the isomorphism given by an equivariant Pontryagin-Thom collapse construction from the geometrically defined equivariant Bordism groups to the equivariant homology theory represented by a specific equivariant Thom spectrum. In these lectures, I will briefly revisit some of the basic results. So typically, my approach will be that I will state precise results now in the more general context of compact Lie groups. But whenever I proved something in class last term for finite groups and the proof is not substantially different for compact Lie groups, when it's basically the same, then I will not give a proof again, but instead I will always give you precise references to the literature. The main reference for this class is my book, Global Homotopy Theory, covered by Cambridge University Press. The book is not exactly cheap, so if you don't want to buy it, you can get an electronic version for download from my homepage. Also, the book contains way too much material to be covered in a class here, so my job is to select some material and make a coherent and consistent story out of it to present to you. Alright, so now we've got the practical things out of the way, and I can go to my whiteboard and explain the mathematics to you. Usually I would be teaching in the traditional way with chalk on a blackboard, but I've decided to use the whiteboard because I think that black on white is probably more readable, and also the screen is smaller so we can get closer with the camera, and hopefully all together it will be easier for you to read everything. Unfortunately, this way I cannot show you the traditional German way of cleaning the blackboard with water, sponge and squeegee, but I guess we can't have everything. Alright, let's go on with the mathematics. As I already mentioned, global homotopy theory studies equivariant phenomena that exist in a uniform and coherent way for all groups, where all groups for us will usually mean all compact Lie groups. In some specific situations, it could also mean a proper subclass, such as, for example, all finite groups. So the idea is that we want to have a setup where all groups act on some topological object, such as a space or a spectrum, in a coherent and consistent way. And there's an obvious issue, namely it's not so clear how you're going to make this rigorous. If, from a naive perspective, the only way one could imagine that all groups act on one object compatibly could be by having them all act trivially, and you could wonder how any interesting mathematics could come from that. My favorite way to formally implement a framework for global homotopy theory is to use orthogonal spaces. So these will be models for unstable global homotopy types, and orthogonal spectra, which will be models for stable global homotopy types. I will give a brief review of the relevant definitions right now. If you really want to have a chance to follow the class, then you're expected to have already seen orthogonal spectra. If that's not the case, I recommend that you go and look at some of the references that you can find on the homepage and brush up a little bit on your knowledge of orthogonal spectra. Alright, let me start with the definition. I will introduce the category of linear isometric embeddings. The topological category L has objects all inner product spaces. So here I need to explain what I mean by inner product spaces. I will usually use this term to denote finite dimensional vector spaces over the field of real numbers that are also equipped with a scalar product, so a symmetric, bilinear and positive definite form. In other words, these are also called finite dimensional Euclidean vector spaces. There will be points where we will want to consider complex analogs of this, and sometimes we also want to consider infinite dimensional vector spaces, but then I will say this specifically. So if I don't say anything else, an inner product space is a finite dimensional Euclidean vector space over the real numbers. These are the objects of the linear isometries category. So now if I have two of those, I need a space of morphisms. So L, V, W is the space of linear isometric embeddings. From V to W. And if I say space, I have to tell you how this is a space, and this has the Stiefel manifold topology. So in a little bit more detail, if you choose an orthonormal basis of the source vector space V, then a linear isometric embedding is going to send this to some orthonormal frame, and it's going to be completely determined by this image. So this way you can identify the set of linear isometric embeddings with the orthonormal dimensional V frames in W, and this is a Stiefel manifold, and this has a standard topology which makes it a compact, closed, smooth manifold. The fact that this has a smooth manifold structure will not be particularly relevant for us. We mostly care about this as a space. It's often convenient that this space is actually compact. That comes in handy at various points. So now I can tell you what an orthogonal space is. An orthogonal space is simply a continuous functor x from this linear isometries category to T, and T is the category of spaces. It's the category of compactly generated spaces. And continuous maps. So I use the terminology compactly generated spaces in the original sense that it was introduced by McCord, which includes the weak Hausdorff condition. Also, most of the time I would just say space, and the details of the point set topology, you can look them up. They won't be particularly relevant for what I explain here, but just to be clear, I work in the category of compactly generated spaces. So these are K spaces or Kelly spaces that also satisfy the weak Hausdorff condition, and this is for me included in the terminology like it was originally for McCord. I warn you that there's lots of references which need to explicitly say compactly generated weak Hausdorff. I'm including this. So an orthogonal space is just a continuous functor. These orthogonal spaces will play an important role later. They will be the models for unstable global homotopy types. But right now, they're just the first step in defining orthogonal spectra. I should also mention that these objects that I call orthogonal spaces, they have been considered quite a bit in the homotopy theory literature, but they often go by different names. So the more common notation for the category that I write L, which, by the way, in all the writings would be a blackboard bold L, just that I cannot draw this here. So this is usually denoted by some version of the capital letter I, and then accordingly, in other references, these are often called I spaces. I use the terminology orthogonal spaces because I want to put emphasis on the fact that they serve as global objects. And also I want to stress the analogy with orthogonal spectra, which are the stable analogs. All right, as I already said, so we will later want to study these in their own right, but right now they just serve as a step in introducing the indexing category for orthogonal spectra. As I said, you are expected to have already seen orthogonal spectra, but they can be presented in different ways. So I will give one specific way of introducing them so that I can introduce relevant notation and fix some terminology. So I will introduce them also as continuous functors on some indexing category with base points, and this will be made from the orthogonal complement bundles. All right, let me introduce this. So if I have two inner product spaces V and W, I write xi V of W for the subset of W cross the linear isometric embeddings from V into W. So this is the orthogonal complement bundle. So specifically, points in here are pairs w, comma phi, with w a vector in w, phi a linear isometric embedding from v to w, and they have to satisfy the condition that w is orthogonal to the image of phi. So this space is the total space of a vector bundle, which is simply a vector sub-bundle of the trivial vector bundle with fiber w. The bundle map is just the projection to the second factor. And the fiber over a point of the base, so over a linear isometric embedding phi, is just the orthogonal complement of the image, which explains the terminology. So from these vector bundles, we'll now make a based space, namely the Thom space. So my notation for this is O of v, comma w. And I define this as the one-point compactification of the total space of this bundle, psi vw, union a point at infinity with the topology of the one-point compactification. And this is also the Thom space of the bundle. So maybe here a brief explanation is again in order. So sometimes Thom spaces are discussed only when you have a metric on the vector bundle, and then often these are defined as the total space of the disk bundle, modulo the total space of the sphere bundle. And that is the definition that works very well in general. In our situation, we have a vector bundle over a base space which is compact, and then the Thom space defined as disk bundle modulo sphere bundle is actually homeomorphic to the one-point compactification, where you just use a suitable scaling function on each fiber that scales the interval 0, 1 to the interval 0, infinity. If the base were not compact, the topologies would potentially be different, and then usually disk bundle modulo sphere bundle is the better definition. But for our purposes, I really want the one-point compactification, because as you will soon see, this is way more convenient for describing all sorts of functor realities. I guess this is the first time where I have to erase the blackboard, so I'll have a short pause. So I can now formally define the indexing category for orthogonal spectra. So the category O, which would be a boldface O in the written sources, has as objects all inner product spaces. As morphism spaces, these Thom spaces. Thom space of the total space of the orthogonal complement bundle. And then composition can be given by an explicit formula. So this will actually be a category that's enriched in based topological spaces, so the right kind of product to consider is the smash product. So composition will be a map from O of VW smash O of UV, where UV and W are inner product spaces, to O of UW, and things have been set up so this is given by an extremely natural formula. W smash phi, V smash psi is mapped to W plus first phi of V, and then phi composed with psi, and you can easily check that this is associative. It has a unit, namely the point 0, identity of V. And I often write these formulas for one-point compactifications. Then, of course, the understanding is that the points at infinity go to the point at infinity. This is the point at infinity is the base point. And there's an implicit claim that this is continuous at infinity, and this will usually be a routine verification that I'm not going to do. So now I have to find this indexing category. The spaces have a topology and a base point, and now we can look at continuous functors, or more formally this would be enriched functors to spaces, and we can define orthogonal spectra. And this is the definition which for me is the most convenient one. So an orthogonal spectrum is a based continuous functor I will often use the notation x or y or something like this, from this indexing category O to the category T star, so which is my notation for the category of based spaces. So compactly generated spaces, weak Hausdorff is understood, equipped with a base point and continuous base point preserving maps. Since we're at it, I can, on the same page, define what an orthogonal G spectrum is. You could define this for arbitrary topological groups. We will only need it for compact Lie groups, so I'll do it in that generality. An orthogonal G spectrum where G is a compact Lie group, is a continuous functor X from the same indexing category, but now to the category of based G spaces. So G T star is based G spaces. So the objects are G objects internal to our category, internal to compactly generated spaces. They're equipped with a base point, which has to be fixed by the group action, and we have continuous equivariant maps that fix the base point. Alright, so this is the basic setup. Now we have all the main definitions on the board. As I said a number of times, you're supposed to have already seen orthogonal G spectra before, otherwise look at some of the references. I will also review a little bit of notation now that goes along with this, and then eventually I will get to the equivariant homotopy groups. But now I have to erase the blackboard again. We've just defined orthogonal spectra and equivariant orthogonal spectra as continuous functors on some indexing category, but I want to make the structure that we actually have a little bit more explicit. So one of the observations is that if you take the same inner product space twice, then the space of linear isometric embeddings is canonically the orthogonal group of V, this group of isometries. The orthogonal complement bundle over this space is trivial, so the fiber is the zero-dimensional vector space everywhere. So if we pass to the one compactification, we basically get the base space with the disjoint base point added. So this is really L of V plus, which is also saying it's O of V plus, so it's the orthogonal group with a composition given by the multiplication in the orthogonal group and the disjoint base point added. And so if we have an orthogonal spectrum, so X in SP, SP is my notation for the category of orthogonal spectra, where the morphisms are just natural transformations of continuous functors. So then, in particular, part of the action is a map from O VV smash X of V to X of V. This is the functoriality when V is the same as W. And so this is really the orthogonal group of V plus smash X of V to V. So the data in particular gives you an action. So X of V supports an action of the orthogonal group of V, fixing the base point. So this is part of the structure that's encoded in an orthogonal spectrum. Another piece of structure is this so-called structure maps. So let me explain those. So here I again have two inner product spaces with a generic notation V and W. So I can write down a certain continuous map from SV. So this is also notation I will frequently use. This is, SV is the sphere of the inner product space. So this is V union a point at infinity, again with the topology of the one-point compactification. I can define a map from here to O of W, comma V plus W in very explicit terms. If I have a vector here, V, I have to give you a pair, a vector in V plus W, plus a linear isometric embedding from W into this. And the vector has to be orthogonal to the image. And this is, of course, very explicit. The vector is little v, comma 0, so that's this V. And then the embedding is the standard embedding of W into the second factor, which I can write as 0 blank, where blank means you substitute the variable. So this is basically the inclusion of the fiber over the preferred embedding from W into the direct sum, and then you pass to one-point compactification. So that's what this is. So now, if X is an orthogonal spectrum, I can use this data to produce the following map. I start with the one-point compactification, smash the value at W. I use this map IV, smash it with the identity. So this gets me to O of W, V, direct sum W, smash X of W. Now I use the functoriality that X has. So I have a W in the source, a V plus W in the target. So this gets me to X, V plus W. And I call this the structure map, and I'll use the notation little sigma V, comma W for this map. So if you've already seen orthogonal spectra before, then there's a chance that maybe they were presented to you in a way that resembles this structure. So maybe they were presented as a collection of spaces X of V with actions of the orthogonal groups and structure maps and some sort of compatibility. So there is an equivalence of categories in the background. Orthogonal spectra can be presented by sort of this structure plus compatibilities, such as associativity and so on. I'm sort of expecting that you know how to pass back and forth between these different descriptions, because we have explained this in detail in previous classes. But I will take the freedom of sometimes defining orthogonal spectra by giving you the explicit data, giving you the values, the actions of the orthogonal groups, and the structure maps. And then whenever I do this, there will be some implicit checks for somebody to do. I have hopefully done them before the class, and you might want to do them after the class, that namely all the various implicit compatibilities are satisfied. All right, it's also going to be convenient to introduce a piece of notation for what I call the opposite structure map, which is where you sort of flip. So here you basically act with a suspension coordinate from the left, and you can act from the right. So this is what I call the opposite structure map. And this I simply define as follows. I go from X of V smash SW. I use the twist homomorphism that flips the two factors to get me to SW smash X of V. Then I use the previously defined structure map, but now for WV instead of VW. This gets me to X of W plus V. And whenever you're in a situation that there are two symbols, such as V and W, that represent mathematical objects, and here they're in one order, and here they're in the opposite order, then some sign of warning should go up that you probably want to insert some symmetry. And that's actually what I'm going to do. So here I also want to act with what I call tau VW, so that's the isometry that just flips V and W. X is functorial for such things, so this gets me to X of V plus W. Now they're in the correct order again, and this composite is the opposite structure map, for which I use the notation sigma V W op. Alright, this is the end of my recollection of orthogonal spectra, and I'll erase the blackboard again. The next piece of structure that I would like to recall is how to evaluate an orthogonal spectrum on a representation. This is very crucial for the equivariant story. So let me quickly remind you how this goes. So let V be a representation of a compact Lie group. And during this class, a representation will usually mean finite dimensional over the real numbers. So the underlying V has underlying an inner product space in particular, so there's a scalar product, and we want orthogonal actions. So we're assuming that the action is by isometries. Of course, if the group is not discrete, we also want that the action is continuous, so the homomorphism that defines the action to the orthogonal group is continuous. And a fun fact aside that you may have wondered if you haven't seen this before is, Lie groups have smooth structures, so why will I often only be talking about continuous homomorphisms? Well, it's just a basic fact of life that a continuous homomorphisms between Lie groups is always automatically smooth, so I don't have to ask for this. One possible reference is the book by Brücker and Tom Dieck, and you will see a reference down here. Alright, so we have a finite dimensional orthogonal representation of a compact Lie group, and then we have an orthogonal spectrum. So let X be, or rather an orthogonal G spectrum. So now we can evaluate x at the underlying inner product space. So x of v has a g times g action. So why is that? Well, you know, x was an orthogonal G spectrum, so it's a G object in some category. So this gives you an action on the x. V is a representation, so that means we have a homomorphism of from G to the orthogonal group of V. And through the functoriality of x, this gives us another G action. And because orthogonal G spectrum really means that G acts through automorphisms of orthogonal spectra, this means that these two G actions commute with each other. So the action on X and the action on V really give us a G cross G action. Now, most of the time in this situation, we will immediately pass to the diagonal action. So, unless, I mean, there will be a small number of cases where I might want to use both actions, but usually we consider X as a G space by the diagonal action. X of V as a based G space, so with fixed base point by the diagonal action. So if we plug in a representation, we get a G space out, and one thing that is really crucial for the global story and to see where the compatibility of all these actions comes from, there is of course the possibility that the action of G on the orthogonal spectrum X is trivial. Still, we can plug in a G representation, and then because here there were two ingredients for the action, we're still going to get a non-trivial G space out, namely from the action on the representation. Even if we had an orthogonal spectrum with trivial G action, that's what we will be doing all the time in the global context. So that's an important detail. Despite the fact that G could possibly act trivially on X, we're going to get non-trivial G spaces out via this construction. All right, if we have another representation, if W is another G representation, then the structure maps sigma VW and sigma VW op are automatically G equivariant. All right. Now I can remind you of equivariant homotopy groups. This is also a very important theme. And now, if I want to really get the story for compact Lie groups also, I have to talk about universes. Universe is also a term in mathematics that's used in lots of different contexts. So I'm not going to use it in the notion of, in the context of set theory here. I'm going to use the term universe in the context of equivariant homotopy theory, so I'll quickly have to tell you what this is. So let me give you a definition. Let G be a compact Lie group. And while there is a more general notion, we will really only need complete universes. So let me just give you that definition. So a complete G universe is an orthogonal G representation which I use math cal U of countably infinite dimension such that every finite dimensional G representation admits an equivariant linear isometric embedding into U. So a slightly sloppy way of saying this is that this G representation, which is infinite dimensional, contains every finite dimensional representation, where contains means, there exists an equivariant linear isometric embedding. So let me emphasize here that I'm looking at vector spaces, representations that as an underlying vector space have a countably infinite basis. So I'm not looking at Hilbert spaces and Hilbert space representations. So this U as an R vector space is just R to the infinity, an infinite direct sum of copies of R. Alright, so now I have to make a number of comments because, when we introduce mathematical objects, we might want to know if they exist and how unique they are. And so here are a couple of things that I have to explain. So the first observation is that, the first fact is that complete G universes exist and are essentially unique. Complete G universes exist and are essentially unique, and I have to explain this. So the existence is easy because I can just write one for you down, and here I'll do it. So existence, I could take U to be a direct sum indexed over lambda, which are irreducible representations, and then I take each infinitely often. So the square brackets mean I take a direct sum over isomorphism classes of irreducible real orthogonal G representations. And then lambda to the infinity means I take a direct sum of infinitely many copies, countably infinitely many copies of each of these. And now we have to use one fact from the theory of compact Lie groups, namely a compact Lie group has countably many isomorphism classes of irreducible either complex or real representations. It's true for both. If the group happens to be finite, there's only finitely many conjugacy classes, isomorphism classes of irreducible representations, and otherwise there would be infinitely many, but they're always countably many. And that means that this really is an R infinity. The underlying vector space is countably infinite dimensional. So if G is finite, we can make a specific choice for this. If G is finite, we can take U to be an infinite sum of copies of the regular representation. So rho G is RG, is the regular representation. So in other words, as an R vector space that has a basis given by the elements of G, G is finite, and they form an orthonormal basis, and every irreducible embeds into the regular representation, so this will in particular allow every finite dimensional representation to embed. In the context of compact Lie groups, there is no good substitute for the regular representation, at least not sort of for this specific purpose. So there is no similar description, and we have to work with this characterization of universes. They are defined by certain properties that they exist. So I also want to make a comment about the uniqueness. I will not write anything down about this. So they're essentially unique. What do I mean by this? Well, there are two different ways in which they're essentially unique. So first of all, they're unique up to equivariant isometric isomorphisms. So any two of them admit a linear isomorphism that's equivariant for the G action and the scalar product. But there's a different way in which they're also unique. They're essentially unique up to contractible choice. So you can consider the space, if you have two complete universes, you can consider the space of linear isometric embeddings from one complete universe into the other one. There's a specific topology on this, a mapping space topology, and with this mapping space topology, the space is contractible. So that's as good as it gets in homotopy theory. So in this way, they're unique, and we're not going to worry anymore about this. Whenever we need it, we're going to choose one. Now that we know what a complete universe for a compact Lie group is, I can remind you of how equivariant homotopy groups of orthogonal G spectra are defined. So for this, we fix a complete universe for every compact Lie group. Fix a complete G universe, and then I'll denote this by U sub G for every compact Lie group G. So now I'll introduce a poset that eventually we're going to take a functor over. So let S of UG be the poset, and that is under inclusion of finite dimensional G subrepresentations of our chosen complete universe. So the universe is infinite dimensional. I'm looking at finite dimensional G invariant subspaces. They're ordered under inclusion. And by the way complete universes were defined, this is basically saying that every finite dimensional representation is one of these V's, well, at least up to isomorphism. So this poset is a way of making precise how we're going to take a co-limit over all representations of the group G, because we have representatives, all of them in this poset. So now we have an orthogonal G spectrum. So let X be an orthogonal G spectrum. We define a functor from this poset to sets. So the functor doesn't need a name. I'll tell you from where to where it goes. It goes from this poset to sets on objects. It sends V to something that I'll write down first and then explain. Alright, so the inner product space V goes to this set. I use square brackets for some kind of homotopy classes of morphisms. In this case, I look at continuous based G equivariant maps from this one-point compactification with induced G action. It's a representation, so G acts. To X of V, which is also a G space, and the way I've previously explained, the diagonal actions from the one on X and the one on V. So these are both based G spaces. Then square brackets indicate that I'm looking at homotopy classes of something. The G indicates that I'm looking at G equivariant maps, and the homotopies have to be through equivariant maps. And this little star is not a grading, it indicates the base point, so it's saying that all the maps have to be base point preserving, and the homotopies have to be constant on the base point. So this gives me a set for every inner product space V. I'm going over the ones which are contained in this complete universe. And now I have to tell you how this is a functor. And so this was a category as a poset via inclusions. So for some V inside W, which is also finite dimensional, contained in UG, both finite dimensional and G invariant, we define a map from SV X of V, G equivariant based, to SW X of W, also G equivariant and based, and we define this map by the following recipe. So an element on the left hand side is represented by a continuous based G equivariant map, and I'm going to send this to a map of the same sort, but now with W, which I define as the following composite. So SW is equal to SW minus V, so this is the orthogonal complement, not the set theoretic complement, smash SV. Of course, strictly speaking, it's not an equality, but the isomorphism is so canonical that I'm slightly abusing notation. So here I can go via the identity on the first factor, smash the map F over there. This gets me to SW minus V, smash X of V. Now I'm going to use the structure map, sigma, for the first space W minus V, and then V. So this gets me to X of, and now if I'm really careful, it gets me to the orthogonal complement of V and W, direct sum V, but this again is so canonically the same as W. Both are subspaces of W that I write some equality here, so I should close the square brackets, and so this composite is what we're sending this to. And let me also introduce a piece of notation that might be useful later. So I write SV minus W diamond F for this, and this means the stabilization of F from the left via W minus V. You can imagine I could also stabilize from the right. I would doing this by switching orders and just using the opposite structure map, so sometimes I would also stabilize from the right, and then I'll just write this in the opposite order. So now there are a few easy things to check. This is only depends on the homotopy class of F, and if V is in W is in another finite dimensional space, that you have associativity, and this is all straightforward. So this is really a functor. So I can get to the main definition of the equivariant homotopy groups now. So X is an orthogonal G spectrum as above. So the zeroth G-equivariant stable homotopy group of X is the colimit over this functor. Pi 0 G-equivariant of X is the colimit over the poset of this functor that I've just introduced as the x of v g star. So slightly informally speaking, I'm taking the colimit of these sets over all representations, just that this slightly imprecise thing over all representations is made precise by this poset. So on the face of it, this is only a set, but on the next blackboard I will remind you of some additional properties that this has, functorialities and structure. So now we've defined the G-equivariant homotopy group as a set first, so let me give you some facts and additional background information without proving this. After all, I proved these things in a certain amount of detail for finite groups in the last term, and the proofs are basically the same for compact Lie groups. So the first fact is that pi 0 G-equivariant of X has a natural abelian group structure So natural is in two ways. So first of all, natural in the sense that it feels very natural. So to do this, you have to choose a representation that has non-trivial fixed points, and then you choose a unit vector and you do a pinch construction. You add maps via a pinch map in some g fixed coordinate. Because we're going to let v grow to infinity anyway, the representations become arbitrarily large. The dimension of the fixed points is eventually going to be 2 and 3, or as long as you have. And then the same kind of arguments that show that higher homotopy groups are commutative show that it doesn't depend on which fixed vector you use to pinch, and that the group structure is abelian in the colimit. Natural also has the technical condition that this is obviously functorial in X. I won't even bother to say how, and then this abelian group structure is natural in X. There is a way to extend this to Z-graded homotopy groups. So Z-graded homotopy groups. The definition is basically the same, and I will be brief. So for k greater or equal to 0, we're going to set pi k g equivariant of X as the colimit, again, over V in sub-representations of the complete universe. And then I take homotopy classes of maps from SV into, take SV plus R to the K. So I add to V the standard standard K-dimensional R vector space with trivial G action. And I map into X of V again. And then this is a functor in very much the same way. And if k is less than or equal to 0, I have to do it slightly differently. I define pi k gx again as a colimit over V in finite dimensional sub-representations of the chosen universe. And then I take maps from SV into X of V plus R to the minus K. And then G equivariant in X. So remember that K is negative, so K is non-positive, so minus K is non-negative, so this makes sense. And the functoriality is, and the abelian group structure, that's all pretty much the same thing. So now I would like to remind you of various properties of the equivariant homotopy groups that we have proved in detail for finite groups during the last term. I don't want to even write down the precise statements again, because they're almost literally, or sometimes really literally the same in the compact Lie case as in the finite group case. So instead what I'll do, I'll have some slides in the video where there will be the precise references for this. The first important property is that looping and suspending shifts the homotopy groups. So there is a way to loop an orthogonal G spectrum, which is pretty much just taking the loop space in every level. Technically, you post-compose the functor that is the orthogonal spectrum with the loop functor. Similarly, you can suspend with S1, so with one-dimensional thing, by post-composing with the suspension functor. And then if you take equivariant homotopy groups of the looped spectrum or of the suspended spectrum, then there's specific isomorphisms to the original equivariant homotopy groups shifted down or up by 1 depending on whether you loop or suspend. The next property that I will often need is that if you have a morphism between orthogonal G spectra, then you can define both a mapping cone and a homotopy fiber by doing the space level constructions object-wise, or you really do them naturally in the functor. There are specific connecting homomorphisms or boundary maps that drop the Z grading by 1, that connect the homotopy groups of the mapping cone in one case and the homotopy groups of the homotopy fiber in the other case, with the homotopy groups of the input spectra, such that you get a long exact sequence of Z-graded equivariant homotopy groups for the mapping cone, and you get one for the homotopy fiber. This is extremely useful for 5-lemma type arguments. The next property that we will need and that I would like to remind you of is that equivariant homotopy groups take wedges of arbitrary many of orthogonal G spectra to direct sums, so a certain canonical morphism is an isomorphism, and they take finite products of orthogonal G spectra to products which are also direct sums because they're finite of equivariant homotopy groups. A direct consequence of this is that the preferred morphism from a finite wedge to the finite product is an isomorphism on all equivariant homotopy groups. The next property is that you also get a long exact sequence on equivariant homotopy groups for h-cofibrations. So I will use the term h-cofibration for morphisms of orthogonal G spectra that have the homotopy extension property internal to this category of orthogonal G spectra, where homotopy refers to smashing an orthogonal spectrum level-wise or as a functor with the interval 0, 1 with a disjoint base point. So then you can formulate the homotopy extension property if a morphism has it. That's what I'll call an h-cofibration. H-cofibrations have the property that the canonical collapse map from the mapping cone to the strict quotient or co-kernel is an isomorphism on all equivariant homotopy groups. And that means you can translate the long exact homotopy group sequence for the mapping cone into a long exact homotopy group sequence for the two input spectra, the map between them, and if it's an h-cofibration for the strict quotient. There's a dual statement. There we have to look at morphisms of orthogonal spectra which are strong level fibrations. And this would mean that for every subgroup H of G and every H representation that you plug in, you get a Serre fibration on the fixed points of the H action on the values of this sub-representation. That's what I'll call a strong level fibration. You can look up the precise definition in the book if you want. And for strong level fibrations, a canonical map from the strict fiber, the categorical fiber, to the homotopy fiber is an isomorphism on equivariant homotopy groups. So whenever we have a strong level fibration, we also get a long exact sequence of equivariant homotopy groups. The next property that I frequently use and that I will just remind you and give a precise reference is that if I have a based G equivariant CW complex, then smashing with that preserves equivariant homotopy isomorphisms of orthogonal G spectra. And this is really the case for the pi star isomorphisms, where you have isomorphisms on equivariant homotopy groups for all closed subgroups H of G. You could replace based G equivariant CW complexes by cofibrant based G spaces if you know about such things, but we would usually need this for CW complexes. If you have a finite-based GCW complex, so with finitely many equivariant cells, or equivalently a GCW complex whose underlying space is compact, then you can also level-wise take mapping spaces out of it, and that will preserve equivariant homotopy group isomorphisms between orthogonal G spectra. So this is a good point to end the first lecture. I have not yet been able to tell you any true global features, but this will come up in the next lecture where I'll get to that. So I would like to thank you for your attention for this first lecture, and I'll see you back next time.